In this video, we'll be going over section 4.7, which is on exponential models. This entire section is based around seeing exponential functions in word problems where they pop up and those sorts of things. So pretty much a lot of what we dealt with throughout this chapter, some stuff from the beginning dealing with exponential graphs, the exponential functions themselves, and definitely last section solving exponential equations is going to come into play here. And for the most part, the exponential model is just that very first thing we learned in this chapter, the exponential equation, but we give some specific letters to it. This is something that you definitely need to memorize. The exponential model formula that I'm going to use throughout this section is y equals a with a subscript 0 called a naught times e to the RT power. All right, this is pretty much y equals a times b to the x, but we're giving special names. Instead of that a, we're calling it a with a subscript 0. The reason why we call it that's so useful is typically when we do a subscript with 0, that's telling us the initial amount. And if you remember way back at the beginning, our a was our initial amount basically. So that's why it's given that name. Now the other parts of this equation, like the b to the x part, it's sort of enveloped in here. But we almost always use e as our base for an exponential model, because this is e is what you use if something is continuously changing, which most things do. But in this question, in this model, t is representing time. Typically, is what we're going to look at, things changing over some set time. It might be days, hours, minutes, years. You just have to be careful about reading the problem, what your time should be. Y represents the amount after time t. So if we plug in t equals 3, y is the amount at time 3. And this could be a lot of things like I have written here. That's why I like to use y instead of something specific. It could be a number of different things. It could be representing population, it could be representing money, it could be representing mass of something, which we'll see quite a bit in the half-life section. A is the initial amount, as I told you. R is called the continuous rate of change. Right, so when your base is e, the exponent has an r in it, and that is the continuous rate of change. The reason why people typically prefer this over the a times b to the x is it's pretty easy to see what's happening because you can compare everything to one formula. If r is positive, we say there is we say continuous growth rate because it's growing, it's going to be positive. If r is negative, then it's decaying. Whatever you're talking about, it's decaying. It's losing mass over time, it's losing money over time, it's losing population over time. And last thing I'd like to mention here, if you've never heard of the PERT formula, that's fine. But this is basically the same formula with different letters as the PERT formula. Ultimately, what all the problems in this section will boil down to is you have to take you need to use this equation, figure out the a0 and the r, because y and t are your variables. That'll give you the equation. And then after you get the equation, you do something with it. You might plug in a t value to find y, you might plug in a y value to find t, but it all boils down to that. Right, so we'll go ahead and look at one of the problems that's going to use this model directly. And I'll just remind you, definitely write it down if you haven't, but I need to be able to view the problem. Okay, so this one we have here, it says a bacteria culture starts with 920 bacteria and grows at a rate proportional to its size. After 6 hours, there will be 5,520 bacteria. What it wants us to do is express the population P after t hours as a function of t. Right? Now, in a lot of ways it doesn't seem like you're told enough information, but this grows at a rate proportional to its size. That is giving you exponential growth. It's telling you it's growing as a percentage of its size. So we're going to use the exponential model. Right, and in place of y, I'm going to use p here for our equation. P, because we're told, equals a0 e to the rt. All right, and remember what I told you at the beginning. If we want to figure out the equation, which is what it's asking us to do here, we want to know what is a0 and what is r. We figure these two out, we plug them in, and that will be our equation. Okay. Now, if we read the problem, it says a bacteria culture starts with 920 bacteria. Remember what we talked about a long time ago, and now also just a minute ago. A0 is representing the initial amount, and we are told initially there are 920 bacteria. So A0 is going to be 920. Now, reading the problem right away, we figured out A0. Okay. The other piece of information we are told is after 6 hours, there will be 5,520 bacteria. We're going to use this to figure out R, but it's not written in the problem. We have to plug it in. This is telling us to plug in time is t. We're going to plug in t equals 6. And we're told the population will be 5,520 at that time. So we're going to plug in p equals 5,520 and t equals 6. And also don't forget to plug in our A0. And we're going to plug in that along with our A0 in our equation. Right, so we got P is 5,520 equals A0, we are told is 920. We got E. R is what we're trying to figure out. And T is 6. Right, so we've got 5,520 equals 920 e to the r times 6, and we want to solve for r. And that's something we are able to do. It's the only variable here. And we know from last section how to go about doing this. We have to solve our r is in the exponent. We divide each side by the 920, get the exponential part by itself. On the right side, we got e to the r times 6. If you want to write it as 6r, which I will do, you can go ahead and do that. It's just multiplication. On the left side, we got 5,520 divided by 920. Oops, quit. That was from last section. 5,520 divided by 920 equals 6. So we're left with solving this. After we got the exponential part by itself, we switch to log form, just like in the last section. Forgot the word to. Switch to log form. We grab our e, brings the base on the other side. Log base e is the natural log. We got ln of 6 equals the exponent, 6 times r. And visually, to finish solving for r, you divide by 6. Right, so we go ahead and divide by 6, and we get r equals the natural log of 6 over 6. Right, this is the exact answer. You could use it as r if you want, or you can type this in your calculator and get a decimal. It's totally up to you. The homework problems will give you specifics. All right, but there's always a concern when you round here that you're not rounding far enough. So if you look at the other part of the problem here, it says give your answer accurate to 2 decimal places in the next part. I'm going to round this to 4 spots. Just make it plenty far. The ln of 6 divided by 6, 0.2986. Right, but once we've got A0, once we got R, that's what we plug in to get our final equation. P equals 920 e to the 0.2986 t. Right, this is the population. P and T are the variables. A0 and R are what we plug in. What we are asked to do, we are now asked with this equation, we're going to use this equation, how long will it take for the population to reach 18,000? So what they're asking for, one thing I like to do is just realize, it's telling you what to solve for and what to plug in. It's asking how long, which means we're solving for t. And it's asking us what is t when our population P is 18,000. All right, so what we do is we take our population formula that we just figured out and plug that in. All right, we're not plugging in for t because we got to solve for that, but we are plugging in for capital P. P is 18,000. Equals 920 e to the 0.2986 t power. And even though we're solving for a different letter, this works out the same way as solving for r last time, because the t's still in the same spot. It's in the exponent. We divide by the 920. $18,000 divided by 920. I'm going to put it as a fraction just because I know what's going to happen here. That fraction's 450 divided by 23. I'll explain why I'm leaving it as a fraction after I plug it in. So we got 450 over 23 equals e to the 0.2986 t power. Keep on moving along solving it. We got the exponential part by itself. Now we switch forms to log form. And we get the natural log of 450 over 23 equals 0.2986 t. Right, so the reason I left this as a fraction and didn't want to put a decimal is because I can plug this in my calculator pretty easily. The less rounding I do, the more accurate my answer will be. But you can type this in your calculator now and then divide it by the number. I'm going to divide it by the 2986 first, get t by itself. And then plug that in my calculator. Right, on the right side we have t, on the left side ln of 450 divided by 23. Is that number? And I want to divide by 0.2986. We divide by 0.2986. We get 9.96 rounded to 2 decimal places. Okay, so it takes that long. If you are worried about the units, you can read the question. It's talking about hours, so this would be in hours. It takes 9.96 hours for this bacteria to reach a population of 18,000. And starting with 920, that's not very long at all. to get that big. If you took this equation and plugged in 120 for t, that would just be 120 hours or 5 days. You might be pretty surprised at what you get for p. Exponential growth, it grows very, very fast. Right, when it comes to using this standard formula, that's really all there is. Right, you have a couple problems in the homework like this. You'll be given some description. You'll be told in some way it's exponential growth, but everything in this section is, which is telling you to use this formula. You will figure out your A0 and your R. You'll plug them in, and then you might have a couple things afterwards to answer. All right, the next section is more specific. It very much relates to exponential decaying, so when our R would be negative. It's called the half-life model. Some of you may very well know what half-life means already. Right. And the half-life of a substance, this is a definition. This is kind of a science definition, but it's useful to write down. The half-life of a substance decaying is the amount of time it takes the substance to lose half of its mass. Okay. So if it starts with 100 milligrams or something, and it takes 10 hours to get to 50 milligrams, that's half. We would say its half-life is 10 hours, the amount of time it took. And there's very much a useful formula here, the way half-life works with R. Right? So R being that continuous rate of change. And it says the following. Let R be the continuous rate of change in the exponential model and T with a subscript H be the half-life. This isn't standard, but I figured it's a time and it's half-life, so H. Then R and TH are related by R times TH equals the natural log of 1/2. This is the one I prefer. An equivalent formula would be R times the half-life is negative natural log of 2. And I just have over here why they're the same. ln of 1/2 is the same as negative ln of 2. But I prefer this one because we're dealing with half-life and the natural log has a 1/2 in it. If you don't like fractions and you'd rather have the negative sign, you can use this one as well. But if you want to, look at the notes. I spent some time deriving the formula for you here. I'm not going to go through it in the video because ultimately we just want to learn how to use it. But if you are interested in how it comes about, I have it done right here. But one thing that's really useful about using this property is if you're dealing with a problem that has half-life in it, which a lot of things do, you can have a much more simple looking formula for the exponential model. Okay, so I got that kind of worded here. Specifically, if you are working with half-life, you can use a more specific model. If A0 is still the initial amount and capital T with subscript H is the half-life, then the formula is Y equals A0 times 1/2 to the power T over half-life. I prefer this. I also have it derived how that works. You plug in the formula for R inside here. And that's something else that if you have a question about, I would be more than happy to explain. But when you're dealing with half-life, this formula is a lot easier to use than trying to use the formula with E in it. Okay, so this one's better if there's not half-life. This one's much better if there is half-life, and that's because the half-life's already in the formula. Right, but we'll have two problems here dealing with half-life to really practice it. The first one, it says the half-life of palladium 100 is 4 days. I have no idea if that's even a real chemical, but what's what we're told? So we're told half-life TH is 4 and our units are days. We don't actually write the units in the formula, but just to keep track of it if you need it. And it says after 20 days, a sample has been reduced to a mass of 7 milligrams. Okay, so this one's a lot like the other one. We are told something about our formula at the beginning, and we are told after 20 days, so after t equals 20, the sample has been reduced to a mass of 7 milligrams. Y equals 7. And the question we are asked in part A is, what is the initial mass? Which is A0, the initial thing. Right. Now, the second I see the word half-life, I'm already thinking about that half-life formula. So I'm going to go ahead and write it down. We got y equals A0 times 1/2 to the t over th, the half-life formula. Now what we're solving for is A0. If you keep track of what we are told, we are actually told a t, a y, and the half-life to plug in. And we want to go ahead and do exactly that. We want to plug all of that in. All right, so we'll go ahead and plug this in to our formula. Y is, sorry, I scrolled off there. Y is 7. A0 is what we're searching for. We got 1/2. T, be careful, use the right T. T is the time, we are told, not the half-life, is 20 divided by the half-life, which is 4. And you'll notice both the times are in days. So that works out. All right, and now you just want to solve for A0. And you want to go about doing that. What you want to realize here, this one's a lot different than the other one. A0 is right here. If you can just simplify this part, then you'll have A0 times something equals 7. You can take care of that pretty easily. So we're going to simplify that. We got 1/2 to the exponent. 20 over 4 is 5. Then if you square, or sorry, not square, if you take 1/2 to the 5th power, right, you can raise each part of the fraction to the 5th power. You get 1 to the 5th, which is 1 over 2 to the 5th, which is 32. And then to finish getting A0 by itself, we multiply by 32 on each side, and that'll take care of that. We'll have A0 by itself because the 32's cancel. And on the right side, we have just A0. On the left side, 32 times 7. If you want to type that in your calculator, which I will just to be super sure, it should be 224. It is. 32 times 7. Our initial mass is 224. And if you're keeping track of the units, I mean, it tells you to use milligrams. That's also told in here if you weren't told that. But the initial mass is 224 milligrams. All right, so the next part asks, what is the mass in milligrams 7 weeks after the start? All right, so let's go ahead and I'm going to write down our formula with our A0 and our half-life plugged in. We have y equals A0 224 times 1/2 to the t over 4 power. All right, y and t are the variables we plug in for the half-life and the initial amount. Because the half-life is like our r. So that's what we're going to use, and now we need to interpret the question to see what it's asking. What is the mass? Well, that's asking for, the mass is represented by y, so it's asking what is y and we're told the time to plug in is 7 weeks. Right, but you do have to be careful here because our problem, the time is in days. The half-life is 4 days. So we have to change this into days because that's already what the units in the problem are. And 7 times 7 is 49. 7 days in a week. Right, so ultimately, this part of the question is asking, what is y when t is 49? We get y equals 224 times 1/2 to the 49 divided by 4 power. 49 divided by 4 doesn't simplify as a fraction. You can type this whole thing in your calculator if you want. Let's see what we get. 224 times 1/2 raised to the 49 divided by 4 power. And we get 0.0460. Well, 0.0460. Which is our mass after 7 weeks. Right, 0.0460. Right. One thing to keep in mind here, if this number seems really weird, it seems really tiny, it actually makes sense because what happens here, this exponent is a little more than 12 if you type it in your calculator, because 48 times 4 is 12. 48 is 4 times 12. So it's a little bigger than 12. What's happened after 49 days is that this number, 224, has been cut in half over 12 times. And when it gets cut in half over 12 times, it becomes very small. Right, but for this problem, that is it. Right, so once again, just to review, when you do problems in this section that are related to the half-life or the exponential model, you need to figure out your A0 and you need to figure out your half-life, or R if it's not half-life. Plug them in, and then based on that information, you're going to plug in something and find something else in the next part. That's really the setup. You figure out the equation, then you use the equation. Okay. So number 2 here is similar. It just works the opposite way. As you'll read, it says, at the beginning of an experiment, a scientist has 260 grams of radioactive goo. After 255 minutes, her sample has decayed to 8.125 grams. Question is, what is the half-life of the goo in minutes? That's the first thing. Yeah, as soon as you see this, like we mentioned before, you want to write down that half-life formula. And like we mentioned before, when we figure out this stuff, we want to figure out what's the initial amount, and for this one, what is the half-life? Well, if you read the question here, we're told what happens at the beginning. At the beginning, a scientist has 260 grams of this goo. It's telling us at the beginning, our mass is 260. Okay. So we've got that. And then the second part, after 255 minutes, her sample has decayed to 8.125 grams. And so when t is 255, our y value, the amount after that amount of time, is 8.125. And we're doing the same exact setup as last time. We plug in everything we have. We're going to plug in t, we're going to plug in y, we're going to plug in A0, and we'll be able to solve for half-life. Let's go ahead and do that. So our y value is 8.125 equals A0 is 260 times 1/2 to the t, which is 255 over th power. And if you kind of think about it, this is the kind of problem where if you wanted to figure out the half-life of something in a lab or something, this is what you would do. You'd figure out how much start with, and then just at a random time later, how much is left. And then you can use your formula to figure it out. Right, but what we are solving for is in the exponent, right? This is back to solving an exponential equation. We need to get rid of that 260, get the exponential part by itself. So the 260, we divide by, see what this is, 8.125 divided by 260. It's not an 8. If you switch it to a fraction, because it is a kind of a nice decimal, you can see that the fraction is 1 over 32. And this equals 1/2 to the 255 over th power. Once you are here, you have two ways to do it. One thing you might notice is that 1 over 32 is a power of 1/2, and you can do the one-to-one property thing, or you can switch to exponential form, log form. Switching to log form always works. These might not have similar bases, so I'm just going to do the switch to log form. So we grab our base, which as a fraction it looks kind of big, of 1/2, and we move it to the other side. We get log with a base of 1/2 of 1 over 32 equals 255 over th, our half-life. And we've talked about simplifying this a few times in our calculator. We can do ln of 1 over 32 divided by ln of 1/2, that change of base formula. And you get 5. And so we've got 5 on the left side equals 255 over th on the right side. And once you're here, you can definitely solve this pretty quickly. Multiply each side by th is one way to do it. Get the th out of the denominator, get rid of the denominator. So we got 5 times th equals 255. Sort of looks like fifth. But we're trying to solve for th, the half-life. We divide each side by 5. And the half-life th, 255 divided by 5 is 51. Right, now this was the question for this part. What is the half-life? The half-life is 51 minutes. But what you'll notice here, we have A0 and we have TH. We can plug them in to make our formula. That's actually what part B is asking us for. It's asking us to find the formula for G of T, the amount of goo remaining at time T. But this is being a little more specific. So instead of Y, we want to use G of T. We take our formula here, we get G of T equals A0 is 260 times 1/2 to the T over half-life T over 51 power. And this is an absolutely perfect answer. You do not need to change it in any way whatsoever. Now, once you have figured out the formula, you can do stuff with the formula. All right, so the part C is just one of those two things that asks how many grams of goo will remain after 71 minutes. So it's asking us to plug in T equals 71. Our half-life was in minutes, so the minutes is good. And it's asking us, what is G of 71? Right, so go ahead and do that. Plug it into our formula. G of 71 equals 260 times 1/2 to the 71 over 51 power. And this is something that I would just do all in the calculator because this exponent doesn't simplify at all. Okay, so we got 260 times 1/2 raised to the 71 divided by 51 power. And that is 99.06, rounded to 2 spots. The units were grams, not milligrams, from the original problem, as you can, I'll show you real quickly, 260 grams. Right, so rounded to 2 spots. After 71 minutes, you got about 99 grams. If you want to make sense of your answer, it does make a little bit of sense. 71 minutes is about 1.5 half-lives, because 51 is 1 half-life, and it's about halfway more than that. And if you think about what's happening with a half-life, after one of them, after 51 minutes, our amount will be 130. If we went 51 more minutes, we'd be half of 130, which is 65. And this is somewhere in between. So it's something that definitely makes sense. The last model we are looking at is called the logistic model. Logistic models are typically very common. Very few things grow exponentially. The reason is exponential graphs that grow, they grow forever. They go up to infinity, if you remember the graph. So I have some background here as to what kind of problems you'll see with logistic models. But I want to show you the shape, the formula, what goes on with them, and then we'll see the problems that go along with it. Most things that have a maximum ability to grow, like a virus spreading, it can only affect so many humans because there are only so many humans. It'll follow a logistic model. Right, so there are a few things to learn about the logistic model. I'll go through the list over here. I'll tell you what's super important. The picture here, I don't necessarily need you to remember these special values. Point of maximum growth, initial value of population, they are nice to know, to use them, but it's not necessarily the most important thing. Knowing the shape and how to work with the equation is what's most important. All right, so the formula for the logistic model, f of x equals c divided by 1 plus a times e to the negative bx. The negative sign here is going to be very specific because what we want in our equation is, what you'll see is c, a, and b are all going to be positive. So this negative sign is important. And if you're talking about time like we were in the last section, we'll probably switch between x and t. The letter C that's representing some number is the most important one. It's called the carrying capacity. Right? And what the carrying capacity is, it's for lack of a better term, it's the most amount of people, if we're talking about a virus spreading, that will get the virus. Okay, so there's a maximum number of people that can get it. You'll see with the very first problem, the question that that really distracted me. The question that we'll deal with is the flu spreading around a town that has a certain population. Its carrying capacity would be the population of the town. All right, A is another number here. It's going to be positive. It's not necessarily the initial amount. In fact, it very rarely will be, because the initial value is given by this weird looking formula when you plug in x is 0. But it is often used to figure out the initial population. Or if you know the initial population, then you can figure out A. But we keep that positive as well. And then B is kind of like our R from last time. It is the exponential rate of growth. Depending on the growth rate, it is necessary that B is positive as well. B is not going to be negative. Okay. So that's another thing to look out for. I just have this labeled here because it's on the graph. You know, like I said, you don't need to memorize this. If you have to use it in the homework problems, I think that's fine. But as far as test questions goes, I'll remind you of the formula for this maximum rate of growth. But what it says is that the point of maximum growth, this one right here, occurs when the population, the y value, is at half its carrying capacity. The carrying capacity is C, half of it is C over 2. And the x value is the natural log of A divided by B. All right, well, we'll begin by looking at a problem where they give us the formula, and it's really just about using this formula. There's not much to this first one. And so it says a certain community consists of 3,400 people, and one individual has a particularly contagious strain of influenza. Assuming that the community has not had vaccination shots and are all susceptible, the spread of the disease in the community is modeled by this formula. A equals 3,400 over 1 plus 3,399 e to the negative 0.65 t. All right, now the important thing that I'm going to point out right away. Serious. All right, so before something popped up on my screen, the one thing I wanted to say, the carrying capacity is in the formula. That's the one thing you definitely want to point out. You will often in the problems be asked about it. The carrying capacity is the top of the fraction here, right? Carrying capacity is C, is the top of the fraction. Now, right away, without doing any math at all, we just see that the carrying capacity is 3,400. Carrying capacity. And in fact, if you just peep down to part B here, what is the carrying capacity for this model? It's 3,400. Now, realistically, not everyone in an entire population will get a particular influenza virus, but for the sake of, simplifying the issues, that's what we're dealing with. Right, but like I said, when you're given the formula, the most important thing is just working with the formula, and it's not a lot different than the last one. Okay. So it asks how many people have contracted the flu after 6 days. So what we are told here is to use t equals 6, and what is A? You plug in t equals 6 and figure out A, because A is the number of people who have contracted the flu after t days. So we get A equals 3,400 divided by 1 plus 3,399 e to the negative 0.65 t. And we're supposed to plug in t equals 6, so let me actually do that. Right, and your graphing calculator, if you have one, is more than capable of doing this whole thing at once. If you want to break it down into the steps, I would simplify the exponential part right here. So 3,399 e 3399 times e raised to the negative 0.65 times 6. Let's just double check we did that right. All right, we have the correct numbers. We press enter. Then in the denominator, we want to add 1 to that. All right, so that is our denominator, and we want to do 3400 divided by that number. This is 3400 divided by, you can retype that in if you, on this calculator, if you hit second and this button, it'll bring up the last number. And we get 48.71. Now, as far as interpreting the answers, because we're talking about people who have contracted the flu and we're talking about people, it would be 49 rounded. All right, it should tell you in the homework how to round this, but since it is people, will use the whole number. All right, so that's one thing you can do with the formula. The other is kind of the opposite. Plug in something for A and solve for T. And I couldn't fit it all on one page, but it says this question here, how many days, the T equals question mark, how many days will it take for the population, or 650 people in the population, to contract the flu? So T equals question mark when A equals 650. Okay. So definitely what might be a little scary is when you initially plug this in, solving for T seems a lot harder than the previous one. So I'll remind you the formula. We had A by itself equals 3400 divided by 1 plus 3399 times e to the negative 0.65 t. And so we plug in our A and we want to solve for t in this equation. Now, all you really have to do is realize if you cross multiply, think about 650 as 650 over 1. It turns into one of the problems like last section. The numbers are a bit messier because it's supposed to be a real life type of problem, and real life numbers aren't very nice. But, you know, that's just the way it is. It's going to be similar question with some messier numbers. So on the left side, we got 650 times this messy denominator, 1 plus 3399 e to the negative 0.65 t. And when we multiply 1 over there, that doesn't change. So that's 3400. But what you want to realize is, as messy as this is, t is up here. If we isolate the t part, we'll get to where we want to go. And at this point, it's up to you. A lot of you may think to distribute this 650 through, which is fine. I'm not going to, just because it's going to make this number very big. I'm just going to divide by the 650 right away. You can do either one. Not one is easier than the other. Whatever you see to do is what you should do. So we do that. We got 1 plus 3399 e to the negative 0.65 t equals, and I'm going to do this in my calculator, but like we did before with problems, if this is a fraction, I'm going to, or it becomes a decimal, I want to save it as a fraction. So we got 3400 divided by 650. Messy looking decimal. If we make it a fraction, we get 68 over 13. Now, I do know that the numbers are much messier than normal, but ultimately it's the same thing. We're trying to get the exponential part by itself. We can now subtract the 1 from each side. That goes away. We got 3399 e to the negative 0.65 t equals 68 over 13 minus 1. For the sake of room, I'm just going to do this in the calculator. We got 68 over 13 minus 1. Keep it as a fraction, and you'll get 55 over 13. Right. Now we've got the part with e by itself. We just got to get rid of the 3399. Now we divide by the 3399. And just to make it a little bit easier to write, we can think about multiplying by 1 on the top, which we don't really write, and 3399 on the bottom over here. That way it's not a fraction inside a fraction. So those cancel out. And this probably isn't going to simplify very much. 55 times 1 is 55. 13 times 3399. 44,187 equals e to the negative 0.65 t. Once again, I understand the numbers aren't great, but this is how numbers work in real life. They're not nice. All right, so now we've got the exponential part. We can switch to log form finally. I'm just going to keep working this way since I'm out of room the other way. When we switch to log form, we get the natural log of that messy fraction on the left side, 55 over 44,187 equals negative 0.65 t. And if we divide by the negative 0.65 to finally finish up getting t by itself, we get t equals the natural log of 55 over 44,187. Type that in the calculator. And we then divide that by negative 0.65. Oops. So divide negative 0.65, and we get 10.291 if we round to 3 spots. Now it says the nearest whole number. Let's just do that. Nearest whole number is 10. And we're talking about days here. And if you think about this problem, that's pretty crazy. 10 days after one person has this flu, 650 people have it. And it's 650 out of 3,400. That's a pretty large percentage. But, you know, this is one type of application. I think this one's very much relatable as far as what's going on with the coronavirus in the world, but also you can kind of think about what I said at the beginning is true. Only so many people can get it. Most things that represent population, physical populations, are going to be modeled by logistic models. All right, so the last one I have here is just a different kind of problem like this. It says biologists stocked a lake with 500 fish and estimated the carrying capacity to be 3,600. Right, let's try to get a little separation here so I don't. Doesn't look like I'm doing something from the previous part. Right, so we've got stocked a lake with 500 fish. That's going to be the initial amount, but remember that's not necessarily our A here. Right, initial is when t equals 0. And we are told the carrying capacity is 3,600. And that's represented by C. C is 3,600. And the next piece of information we are told is the number of fish grew to 640 in the first year. So t equals 1. It's telling you right here in the problem, find the equation after t years. T equals 1. The population, which they're asking us to use p, is 640. And they want us to find an equation. And you got to write down the equation for the exponential, or sorry, not exponential, logistic model. The one with the carrying capacity. We have p of t in place of y, because that's what we're told to use, equals c over 1 plus a times e to the negative b t instead of x here. So we want to make sure we write down that formula and just get right. If you write it down when you do the problems, that's the best way to try to memorize it. And what we need to figure out in this problem is what is A, what is B, what is C. And I'm just writing them in the order they're written in the problem, but we are told C is 3600, 3400 was the last problem. We are told C is 3600 in the problem. That's the carrying capacity. All right, so what you want to do first is plug in the initial information. And that'll allow you to solve for A, as you will see. So plug this in. You know the initial population P of t equals 500 with t equals 0. And we're also going to make sure we plug in the C value we're given. So 500 equals C is 3600 over 1 plus a times e to the negative b times t, which is we're using as 0. Now at first this also looks really bad, but what do we know about anything raised to the 0 power is it is 1. E is being raised to the 0 power, so this equals 1. Right, negative b, whatever b is, we're multiplying by 0. So the exponent there is 0. And we get 1. And just to simplify, we got 500 equals 3600 over 1 plus a. Now go ahead if you want to write the 500 over 1 so you can see we can cross multiply. And we got 500 times 1 plus a equals 3600. All right, now this is much the same way as the last one. You can divide by the 500 or distribute and go about that way. I'm going to divide again just because in general it'll allow you to have smaller numbers. We've got 1 plus a equals 3600 over 500. And if you leave that as a decimal, since it's 7.2, it's a nice decimal, that is fine. 7.2. And subtract the 1 to get a. We got a equals 6.2. And that's another thing we want to solve for. Remember, we need A, B, and C, and we got A and C now. So the last step to get B is to use the only piece of information you haven't used yet, which is this. We're going to plug in A and B into our, A and C into our formula because we figured out those. And we're also going to plug in T equals 1 and P equals 640 to get B. So plugging in absolutely everything. T equals 1, P equals 640. C equals the 3600 that we already plugged in before. Just don't forget to do it again. And A is 6.2. And we're plugging it into our logistic formula right there. Okay, so let's go ahead and do that. P, or P of t, is 640. equals C, which is 3600, over 1 plus A, which is 6.2, times e to the negative b times t, which is 1 power. We're using t equals 1. I'm going to go ahead and just simplify. Really, the only thing to simplify here is multiplying by 1. So I don't need to rewrite a whole step for that. But we will solve this the same way we solved the previous one, the same way we solved the one before that. Cross multiply. Get rid of that fraction. Always a good idea. Get rid of a fraction. So we go ahead and we cross multiply. We get 640 times the 1 plus 6.2 e to the negative b equals 3600. So we're just multiplying that by 1. Once again, I'll reiterate the same thing as last time. You can distribute the 640 or just start by dividing it, and I'll divide it. I can assure you, as long as it did take last time, it's not going to be any quicker the other way. So we got 3600 divided by 640. Yeah, 5.625 is a nice terminating decimal. You can use that if you want to switch to fraction. 45 over 8, it's up to you. I'll use the decimal here. Since it terminates, we got 1 plus 6.2 e to the negative b equals 3600 over 640 was 5.625. Right, now we get the exponential part by itself. We subtract the 1. Subtracting 1 here is pretty nice because of the decimal. We got 6.2 e to the negative b equals 4.625. Then we divide by the 6.2. Rid of that, we get e to the negative b equals 4.625 divided by 6.2. Probably won't really simplify very well. Let's see. Yeah, it's a messy decimal. We don't want to use that. And the fraction's not that great either. I would honestly just leave it like this. 4.625 over 6.2. Right, now once we have the exponential part by itself, we do the natural log on the other side. We switch to log form, and we get negative b equals the natural log of 4.625 divided by 6.2. Now we can go ahead and type this in our calculator because it's just negative b. If we change the sign after we type it in, we're good. So we type in the natural log of 4.625 divided by 6.2. We get negative 0.2931. So negative b equals negative 0.2931. And to get b, we can just knock the negatives off of each other. So b equals 0.2931. Clearly didn't leave enough space to do this part on the notes. Right, but finally we've got A, B, and C. And I'm just gonna plug in our A, B, and C that we found below here, and I'll box that in as our answer. Our B was 0.2931. Okay, so we've got this C, we've got this A, we got this B. When we plug them in here, we will have our final answer. P of T, our formula equals C, which was 3600, divided by 1 plus A, which was 6.2, E to the 0.29 T. Just round however far it says to round in the problem. Right, that is the answer to part A, and that is absolutely as challenging as that can get. So we have the formula. More practice with that. And once again, let me box this stuff off. The next part here is just figuring out how to use the formula for that special point. It says, how long will it take the population to increase to 1800, which is half the carrying capacity? So I'm gonna go ahead and scroll up to the original picture and remind you, when it's at half the carrying capacity, the time is the natural log of A over B. So when we figured out A and B already, we can actually just use what we got, plug in A, plug in B, and go from there. Since it's half. If this was any other number, you would not be able to use this, but intentionally this is half. You are told it's half. T is going to be the natural log of A over B. A was 6.2. B, I'll use the 1 rounded to 4 spots just because I have room to write it. ln of 6.2 divided by 0.2931. That equals 6.225. And that's how long it will take. Remember the problem, if you've forgotten at this point, the problem we are asking is talking about fish in a lake. It starts with 500. It has a carrying capacity of 3,600. You know, the reason why this makes sense is if there's too many fish in one lake, then there won't be enough food for them and some will die because they'll compete for the food and they'll go hungry. Some of them will go hungry. So that's pretty much a natural reaction. But it will take a little more than 6 years for the population of the fish to get halfway there. So plenty of time. It grows pretty slowly. Right. But that is logistic models. Logistic models are very, very common in nature as well.